Critical Thinking Rule 20, work towards the most likely explanation. Rule 20 is about giving you tips for how to figure out which of many proposed explanations for a correlation is the most likely. An explanation generally involves a causal claim. So first you can try to find more information about the correlation to see if other people have looked into this question more deeply. You can use internet searches, but be sure to use the rules and tips for finding reliable sources from Chapter 4. You can also use research databases such as EBSCO, JSTOR, ProQuest, or Google Scholar. This will give you access to scientific studies on the question. So for example, if you wanted to know whether eating red meat causes health problems, you could first start by looking at general references available on the internet, perhaps such places as Medline Plus or Wikipedia, and then you could go search for actual scientific studies in research databases. Secondly, there should be an identifiable causal mechanism that could, in principle, link the observed variables. If you look at the example of the coincidental correlation between the expanding size of the universe and the expanding money supply, as represented by inflation, this is known without having to do much research to be a coincidental correlation because there is no known causal mechanism that could link the two. Conversely, in the case of eating red meat, there could be various physiological mechanisms connected to the organic substances available in red meat and various health outcomes in the body, such as saturated fat having metabolic or other influences on the human body. So what you want to do is try to identify causal mechanisms. This is generally something that's best left to the scientists, but you can look to see if other people have commented on possible causal mechanisms linking the two. This, for example, is one reason why it's fairly easy to dismiss vaccination claims, and the idea that vaccines cause bad health problems. This, of course, is in principle possible. You can't rule it out as easily as you could rule out the connection between cosmic expansion and expanding monetary supply. However, unless people who propose that vaccines have a particular negative health outcome can identify a causal mechanism that plausibly links the two and then test it, it basically doesn't have good evidence to support it. Thirdly, look for converging lines of evidence that lead to the same causal conclusion. So if you have multiple sources or multiple lines of inquiry with different methodologies and assumptions that confirm the same hypothesis about a causal claim, that really lends increasing probability that that claim is true. So let's talk about how to evaluate different types of scientific studies and how they relate to evaluating causal claims. Not all scientific studies are equal in terms of their level of justification. At the lowest level, we have an observational study. This is better than nothing or just informal observation because it does have some kind of control or systematic nature to it. It's data collected and tabulated, but there's no control or experimental group. That just means that you look at a certain phenomenon. You look at people who eat red meat, and then you look at their health outcomes to carry on that example. This has no control because we don't know what the people would have been like in terms of their health if they had not eaten red meat. Even if you have in your study people who do and don't eat red meat, you don't know if the people who eat red meat have worse health for other reasons. Maybe, for example, if you're more likely to eat red meat, you're also more likely to smoke or drink alcohol or eat or do other things that themselves impact your health. An experiment helps you rule out coincidental correlations between variables and to try to identify a deeper causal connection. So in an experiment, data is collected both from a control group and an intervention group. The control group is the one that does not get the experimental intervention. The intervention group does. For example, if you wanted to test the effects of eating red meat on health, you could start by people who don't currently eat red meat. Some of them would not be allowed to eat red meat, and then others would be forced, quote unquote, to eat red meat as part of the experimental intervention to see if it has any effects on their health. Or you could go in the reverse direction. Start with people who already eat red meat, then some people are allowed to continue, Others are not allowed to continue. And ideally, you would want to look at this over a long enough time period to see if it has effects on health, because if there are health effects, it probably would not manifest immediately. A randomized controlled trial is even better than a basic experiment. It's an experiment in which the subjects are randomly assigned to the control or to the intervention group. So that way you avoid the risk of self-selection bias. If people can choose whether or not they're getting the experimental intervention, then that could introduce the possibility that people who want to choose that have some other factor that could explain subsequently observed variation. With the RCT, it rules out that possibility. There's also the importance of studies which replicate or fail to replicate the results of previous studies. A replication is a scientific study that attempts to repeat the results found in a previous study. This is very important because just because a scientific study finds some results, it doesn't mean that it's going to be replicated successfully by other scientists or teams. There's always a possibility that a scientific result was gotten through chance or through some methodological flaw. And if you look at the standard for judging what's called statistical significance, this means that if there's no actual relation between the variables being studied, then there's only a 1 in 20 or smaller chance of seeing the effect that was observed. So this is used to establish that there's an actual relation between two variables being studied. But this criterion, even though it's quite helpful, doesn't absolutely rule out the possibility of a coincidental correlation. And this can sometimes operate with researcher or publication bias. If there are 20 or more teams of scientists studying a given issue to see if, for example, there is a correlation between eating red meat and negative health outcomes, suppose one out of those 20 groups finds that eating red meat results in negative health outcomes. That might be the only result that's published. The others failed to find an effect, there was no correlation, and so either they didn't bother submitting it or it was submitted but not published. This is just a hypothetical scenario, but it shows you how these sorts of things can happen. That's why with the result being published, it can be helpful to replicate it. Failure to replicate should decrease our confidence in the results of the original published study. Do note that failure to replicate does not absolutely falsify the previous study. It just means that we're less likely to believe it to be true. Finally, a meta-analysis summarizes and analyzes data from all or most or the best previous research on a question. So you could think of this as the highest quality of scientific study, and that it's looking not just at one actual experiment or observational study or whatever, but looking at dozens or hundreds of them and trying to make a general conclusion. Also, beware of human cognitive biases when assessing causal claims or making causal claims yourself. The human mind is more likely to make certain types of causal connections or to be biased in support of certain types of causal explanations, regardless of the actual evidence. One is the agent detection bias. This means that we favor explanations involving human-like agents or choosers as causes. You can see this, for example, in the popularity of conspiracy theories, ghost stories, tales of divine intervention, and aliens. In each of these cases, we have a group of people, as in the conspiracies, or human-like beings, albeit with supernatural powers, such as ghosts, gods, or aliens, that are intervening in our world for a certain goal or motivation. So the human mind seems to have a very strong tendency to try to explain phenomena in terms of humans or human-like beings performing actions to fulfill some goal of theirs. And we can see this in many other spheres as well. So if the stock market crashes, there's a tendency to view that as a result of a conspiracy as opposed to just a series of errors. I mean, either explanation is possible, but the human mind strongly prefers the conspiracy explanation. It's much more satisfying psychologically, which is not to say that conspiracies never exist or that ghost gods or aliens are impossible. It's just to say that we're going to be biased in support of explanations that are in those forms. So if you use ancient aliens to try to explain various not yet understood archaeological finds, or other geologic phenomena, this could be a bias towards agent-based explanations. There's also the availability heuristic. This means we tend to favor explanations involving causes that we're familiar with, that come easily to mind. Another type of cognitive bias is confirmation bias. This means favoring explanations that confirm our pre-existing beliefs. So if we already believe in an alien story or in a conspiracy theory, then we're going to try to find additional evidence to confirm that. Or we're more likely to interpret new ambiguous phenomena in terms of this theory that we already have a preference for. Next up, Rule 21, expect complexity regarding causal explanation.